Hello everybody. Thanks everybody for coming. My name is Andrew Duncan, a lecturer at Imperial College, and also a group leader at the Alan Turing Institute. And today I'm going to talk about the geometry of Stein variational gradient descent, and if I'm lucky, some other related ensemble methods which I've been working on very recently. So thank you very much for the introduction. I'm really happy to be talking today. And so this is a joint work with Nicholas Nusken, who's currently based in Potsdam, and Lucas Zbruck, who is also based at the ATI and also at the University of Edinburgh. And so before I get into the methodology, let me provide, for those who maybe have not seen these methods before, let me provide some very high-level motivation and then move forward from there. So the probably the most familiar motivation is that of Bayesian inference in high dimensions. So it's the usual setup. Suppose we have some data y and we have some model for that data parameterized by some unknown parameter, say x. Then if we have access to a likelihood for y given x, then if we impose a prior on the unknown parameter x, then of course Bayes' rule gives us an expression for the posterior distribution. And a typical activity is basically to somehow characterize the posterior distribution. So this, what that means depends highly on context, but in most situations, unless you have a closed form, you wish to generate samples from this distribution and perhaps compute expectations with respect to the posterior density x. And so where is the challenge? The challenge is, of course, that we are often in we're often in very high dimensions, and that forbids us typically, and typically we will only have access to the posterior up to a normalization constant. And computing that normalization constant such that this integrates to 1 would be as expensive as often the problem that you're trying to solve originally. And of course, this is a very familiar problem and is motivated various classical approaches. Of course, the most classical one is MCMC in this context. So the idea is that we produce a Markov chain which has, as its unique invariant distribution, the density that we wish to sample from, and we run this chain, and if we choose the kernel of this Markov chain in the appropriate way, then we can get away with not knowing the normalization constant of our density. And of course, so the advantages of this approach are that is asymptotically exact, meaning that in the sense that if I generate, I can, if I want to compute, for example, some expectation of a quantity of interest q, I can get within arbitrary accuracy if I produce enough samples, if I'm willing to spend enough computational expense. The disadvantage is that convergence is slow. The chain is not producing independent samples, producing correlated samples, and unless I'm doing something very clever, this correlation is to our disadvantage. And so this has motivated other approaches where we trade off the asymptotic exactness for speed, basically. So we lose that exactness, but in return we obtain some speed. So there, of course, there are various approaches, but I'm going to talk about a very specific paradigm. And so this is the idea of doing inference using deterministic maps. So what? Okay, so before I go on, if anybody wants to ask some questions, please just go ahead and ask. It's probably, I probably won't be able to see the chat. So if you just, shout anytime during the talk, I'm very happy to answer any questions. You don't have to leave them till the end. So the idea of inference via deterministic maps was, I first saw it in this context, at least, in the work of Moselhi and Marzouk in 2012, and the idea is very straightforward. if I have some initial distribution which I can sample from very easily, for example, maybe the prior distribution in my model, then I would want to learn a function, basically a vector field, or transformation map rather, T, in such a way that I can basically transform this distribution into this distribution. And if I can somehow learn this transformation, that's really good, because once I can do that, then provided I can really easily generate independent samples from my original distribution, then I can quickly generate independent samples from my target or posterior distribution. And of course, the ambition here, the ambitious part is actually learning this function T. And in the paper of Mozehi and Marzouk, they delineated a general strategy to doing so. And so the idea is, of course, oh, sorry, just a second. So the idea is basically to learn a deterministic map which pushes forward prior to posterior. And of course, this is if one doesn't restrict the class of functions to look over, to search over for such a configuration, this becomes quite an intractable problem. And so what they did in the paper, they exploited certain structure in the map. Specifically, they exploited the Noth-Rosenblatt rearrangement as a representation of the transport map. And what's nice about this paper and is that they formulated the problem as an optimization problem, so that the problem has a variational characterization. So what they're looking for a transport map T in an appropriate class of functions, which such that you're minimizing the Kullback-Leibler divergence between the push forward of your map under this transformation and your target distribution pi. And so basically the challenge then is to solve this this optimization problem in an appropriate way. And so that was the goal of that paper. And
can I just ask a question?
Please, yes.
So on your previous slide, you had a nice circle, and
Yep.
that's getting mapped to the TX. Are you saying that this circle you don't actually have choice over? That's the prior that you're trying to map?
It doesn't have to be.
Okay, so
it can be anything.
So it could be just a normal.
Yes, exactly. Yes.
Okay.
I think in the problems that they were considering in that paper, the prior was always very nice, and so it made sense. But of course, I think you have very strong control over what you can pick there.
Okay, thank you.
Thanks. And so they formed it as this nice optimization problem, and then the paper really focused on how to actually solve that in practice. And so that was the first time I saw this general idea. And then in 2016, another idea in the machine learning community popped up with an idea which is spiritually similar. And so the idea is basically, rather than again, we have this deterministic evolution of these say particles. What's a little bit different in this situation is that rather than trying to find a map which goes from some initial distribution to the target, we really look at this composition of lots of deterministic maps that each one infinitesimally pushes you a little bit closer to the target distribution. And so basically at discrete times, particles are updated by moving them along this map T of x here. So what T of x does, so it's basically the identity plus epsilon, which is some step size, for example, times a vector field. And so what it's doing, it's basically pushing each particle a small distance along the arrow dictated by the vector field at that position. And so this was the paper of Liu and Wang, and they called their method the Stein variational gradient descent for reasons that I will mention in a little bit. But so again, they also had a variational formulation. So they also reformulated their problem as an optimization problem. And so what they did is they of course, at every step, they needed to find their vector field, which would take them a tiny bit closer to the target distribution. And so rather than trying to minimize directly the KL divergence, what they did is they said, okay, let's find the vector field which maximizes the rate of decay of the rate of decrease, rather, of Kullback-Leibler divergence between the pushed forward distribution and the target distribution. And we will so basically we will look in some class C of sufficiently nice functions, which to be chosen in a bit, and so the resulting variational problem becomes this. So in some sense, rather than try to solve to optimize over KL, we try to optimize over what you could consider a derivative in some sense. So you're looking at the rate of change instead. And this was a very good idea for a simple reason. So it turns out that if you compute this derivative and you evaluate it at epsilon equals 0, so you get the rate of change, the infinitesimal rate of change, then this actually has a closed form, at least up to expectation. In fact, it's going to be the expected value with respect to your current distribution, say rho, of an operator S pi applied to your vector field phi. And S pi turned out to be what we call the Stein operator. So associated with pi, or maybe the Longevan Stein operator, if you want, I don't know. There's so many different names for this, but basically it's this expression here. And so just for those that maybe want to make a connection with other fields, if of course I replace my phi, my vector field, with say the gradient of some function, say I don't know, grad of g, right, and I plug it in here and here, what I will get is an operator which acting on g, which is just the infinitesimal generator of the classical overdamped Langevin diffusion process, which is what you can use to also sample from the target distribution. And so the key point here is that this, by having, so the only point at which pi enters is through here, and there's no dependence on the normalizing constant. And so the variational problem then becomes to find phi, which maximizes this quantity here. And so this term here, the maximum, so the supremum here, is what we call a Stein discrepancy. And so it's named after Charles Stein, who used these originally. I think the original paper was in 71, if I remember correctly. And so Stein discrepancies are a way to basically bound above and control distances between probability measures. So they're used classically as a way to quantify, for example, the rate of convergence of a central limit theorem to the actual normal distribution at which it's converging, and it's been widely studied since then. And so basically then the key point, all that's left, is to find a way how to solve this optimization problem here. And the natural approach, of course, in this context is to exploit something like the kernel trick. And so that's exactly what the authors did. They chose C to be the unit ball of a vector valued reproducing kernel Hilbert space associated with this kernel here. So basically this set here of vector fields. And then exploiting the kernel trick, then you can actually get an expression for the optimal vector field, and it's going to be up to, again, it's a closed form up to expectations. And the key point here is that this doesn't depend on the normalization constant of the target density. So that's a very attractive approach. And so if you basically then assume that rather than have access to an initial density Q, you have access to a set of points, then you can write, this basically gives you an update rule to describe the evolution of these points. And so if I, and I'll do this throughout this lecture, I'll just write V as minus log pi. That's just, being a physicist a little bit. So V is the potential. You can then write down an update rule for every particle going from time n to time n+1 in this way. Okay, and so basically, if just as an example below, if I want to sample, if my target distribution is this contour plot, which is this double kidney type thing, and I start from an initial distribution which is a Gaussian in the middle, then if I simulate that with this dynamics, that's what I see basically. I see this process, and what you'll see, I just maybe there's a tiny bit of a spoiler. While like the, let's see if I can do that again. So you might see that while like the bulk of the particles go very quickly to, you know, the two modes of the distribution, there's a lot of like latent motion, slow motion at the tails of the distribution. And that's an important point. That's an important thing to keep in mind when we're talking about speed of convergence. And so I'll revisit that later, but I just wanted to show you visually that thing. So in fact, it's still, you know, well, there's still some little bit of motion, you know, in kind of the tail part of the distribution. And so, of course, one could study the discrete update rule directly, but you know, there's not much. I think there's not much you can say really. Well, that's not true. You can say quite a lot actually, but in some sense, it makes sense to look at various limits in which you can simplify the behavior. And so the first obvious limit would be to rescale time, and rather than have an update rule, just take the step size to go to 0 and look at this as a continuous time process instead. And so by doing so, you obtain this this system here of coupled ordinary differential equations. And for each particle, you get this ODE, which has two terms. So the first term is this one here. Well, actually, let's start from the second term. So the second term here, it's basically a kernel weighted average of the minus grad pi, and that's actually the gradient. So minus grad pi is actually gradient of log pi, basically. So what this is doing, it's basically moving particles towards the modes of the distribution. So it's going to push you towards the local mode, depending on which basin of attraction you're in. This term, however, on the other hand, what it's doing, it promotes repulsion. And so if two particles get very close to each other, this is suddenly going to become dominant. And this was very interesting, because what that meant was that, let's say, well, what one would think is that if you have many particles, then let's say you have, so one of the hardest problems in MCMC is when you have multiple modes. And so you need your sampler to spend a lot of time in one mode before, well, it will spend a lot of time in one mode before it goes to another. And so what this approach kind of suggested is that if you had a lot of particles in one mode and another particle came along, it would be discouraged to explore that mode and would rather search for other modes instead. And that would promote superior exploration of your sampler at the cost, of course, of, you know, having to deal with all the coupling. And so this, you know, this made it very attractive as a prospect for sampling from such distributions. And so we were quite keen to understand whether that's true, because if that's true, there was the possibility that this might even be, for example, could potentially be much more competitive than, say, you know, standard MCMC. And again, so we decided to take another simplifying limit, because working with a coupled system of ODEs is quite challenging. So instead we said, let's take the number of particles to go to infinity. And so then we no longer work with a set of particles. Those particles lose their identity, and instead they just treat them as a density, as like a you know, a density of particles. And we call that density of particles at time rho t. And so rho t will satisfy, it won't satisfy an ODE anymore. It will satisfy a partial differential equation. Actually, it's a very nasty one because it has integrals in it, so it's non-local, and it's also non-linear. So this is not a very nice partial differential equation to work with. But nonetheless, it's still easier. You can still extract quite a lot of insight out of this, and I'll explain why in a bit. So one important property that immediately, surprisingly, follows from this representation is that if I look at the rate of change of the Kullback-Leibler divergence between rho t, the density at time t, and pi, well, that's actually always decreasing. And it's decreasing at a rate which is determined by the Stein discrepancy between, actually the kernel Stein discrepancy, I should have written, between rho t and pi at that time, squared. And so in a paper by Liu and Nolan, 2018, they actually derived rigorously this mean field limit, and they showed that under appropriate initial conditions, that rho t is going to converge to pi as time goes to infinity. And that's good, because that means that at least in the infinite particle limit, it's sampling, it's asymptotically exact. It's going to converge to the right distribution. And of course, then by choosing less particles, by having finitely many particles, you're an approximation. But in some sense, you would expect that if you have sufficiently many particles, then you're in a real regime where you're approximating pi well. And so the question that we were curious about is how fast is this convergence? Because in some sense, taking, for example, if we take the field of Markov chain Monte Carlo, much of the effort is dedicated towards understanding and analyzing the efficiency of various algorithms under various conditions on the target distribution. And we felt that we should also understand, at least, under some simplifying assumptions, the performance of this method in a similar context. And so the question, therefore, is, can I establish a rate of convergence? How fast does this converge? Now, if, for the sake of argument, I could show that I had a property like this, so that the Stein discrepancy squared between rho t and pi was somehow greater than lambda, with lambda some positive constant, times the KL divergence, I would be in a really good place. Because if I do have that property, then just using the equation from the previous page, I can of course write down the rate of change of this divergence to be less or equal to minus lambda times the Kullback-Leibler divergence, just by substituting terms. And then I can use something like Grunwald's inequality, and I immediately get that I have an exponentially fast rate of decay towards 0 in the Kullback-Leibler divergence. So rho t, the KL divergence between rho t and pi is going to 0 asymptotically quickly. And so it's converging asymptotically quickly in this respective divergence. And so that would be a really good situation. And that's kind of the reason I brought this up is, of course, this has a very natural analogy, which is very well studied in this field, and that's namely the logarithmic sublevel inequality. And so this is slightly different. This inequality is that the Fisher information between rho and pi is greater or equal to, say, lambda times the KL between rho and pi. And so that's, if that holds for all rho, then we say that pi satisfies a logarithmic sublevel inequality. And so just to be clear, this is a property of pi. It's nothing to do with the algorithm which you use to sample. It's purely an intrinsic property of pi, which is determined by its, how its curvature, its, how it behaves in the tails, etc. And so J here is the Fisher information. And so why do I bring up this connection? Well, let's take another system, or another system, a stochastic one now, which we can also use to sample, and that's, of course, Longevan dynamics, or more specifically, overdamped Longevan dynamics. And so that's described by a stochastic differential equation, which is going to be in this form. And so I have the drift term, which is pushing me towards the mode, the local mode, and I have noise, which is going to be basically Brownian kicks with the right variance. And so associated with xt, the particle at time t, I have, of course, a density, rho t. And in this context, I can also show a very similar inequality to the SVGD case, that the rate of change of Kullback-Leibler divergence between rho t and pi is going to be minus the Fisher information. And so in this context, if I did have a logarithmic sublevel inequality, then I would get exponential convergence of rho t to pi in Kullback-Leibler divergence. And so and then one might ask, so what conditions do you need to get a logarithmic sublevel inequality? Well, there are various results that one can use, but typically, for example, there's a theorem called the Bakri-Emery theorem, which basically tells us that if the negative, if pi is log concave, so the logarithm of pi is concave, then that's sufficient for a logarithmic sublevel inequality to hold, and then this condition hold. And so the question is, do I get similar conditions for SVGD? So a set of nice conditions which I can use, maybe the same, which I can use to establish when exponentially fast convergence does hold for SVGD, and using Longevan as a benchmark. And so basically it made sense to compare these two. And I mean, looking at them, they seem to be very, very different beasts, in the sense that, Longevan is effectively a stochastic differential equation, right? SVGD is literally, it's a deterministic system, either an update, let's just say it's an ODE, a system of ODEs. If we look at their densities, rho t in each case, one is determined, actually has a nice linear local associated PDE, known as the Fokker-Planck equation. The Stein case has that horrific thing that I showed before. And so the question is there anything in common that I can use to study the rate of convergence of SVGD? And it turns out there is, because both Longevan and SVGD, turns out, can be expressed in a very similar fashion. Because it actually turns out that both of them can be expressed as gradient flows of a loss function, specifically KL divergence, but with respect to different geometries or metrics on the space of probabilities. And so let me explain what I mean by gradient flow. Specifically, let's say I am at, let's say I discretize time again. Let's say I am at time index n, then and I want to go to time index n plus 1, then the density at n plus 1, rho n plus 1 is going to be the minimum of the KL divergence between pi and rho, regularized or constrained such that the distance, in an appropriate sense, to the previous step is sufficiently small. So basically, I have this epsilon here that acts like my step size, so to speak, and basically this is constraining it such that in this distance, rho n plus 1 doesn't go too far from rho n, but it's still moving in the right direction. So that's a gradient flow formulation. And it turns out that SVGD has exactly the same formulation. What's different here is that the distance with respect to which we constrain ourselves to be close to the previous step is different. And so in fact, the distance here is what we call for Longevan is what we call the optimal transport distance. But in the SVGD case, we have something which is dk, and dk I'll present in a bit. Is what we call Stein geometry. So it's a different geometry, and so these are basically two different. They're optimizing the same loss function, but in some sense, the directions in which you can move to optimize are different. And so that will give rise to different trajectories. And so maybe an illustration can be seen down below. If you imagine this is your loss function KL, and in some sense here is the search space. You can think of one as having a search space that looks like this, and another one where you have this there's crinkles and bumps, and so it's not clear how you can, you might need to negotiate like some sort of crevasse or something to get to the same point that you could do, that you could have maybe crossed directly to in the first gradient flow. And so okay, so let's talk a little bit about these two distances, because clearly they're going to play a role in the rate of convergence. And so so let's maybe talk very briefly about the optimal transport distance, or the Wasserstein distance. So how is this characterized? Well, so there are various ways to define Wasserstein distance, but the one that makes most sense in this context is what's known as the optimal transport characterization, or the Benhamou-Brenny formulation, so to speak. And so we define, given two probability distributions, mu0 and mu1, we define the distance to be basically the minimum of the integral of this norm over Vt, or the norm of Vt, of Vt. And Vt is a vector field. And the constraint that we have is that mu-t, and mu-t is an associated trajectory of measures such that mu0 is equal to mu0 and mu1 is equal to mu1. And basically, we have this constraint here. And what this constraint means, this constraint here, is basically describing the evolution of probability from mu when t equals 0 to mu when t equals 1, pushed along by this vector field Vt. If I want to relate it back to the push forward idea that we were talking about previously, you can think of Vt as like the gradient of the local transport map. And so it's important that we cannot simply just put an arbitrary transformation from mu0 to mu1, as that every time we have to make sure that we're still a probability measure. And so this relationship, this constraint, guarantees that for every t, mu-t is of course non-negative, and it's of course it integrates to 1. So there's no loss of mass. And so basically, this describes a search over all possible such vector fields which transport mass from mu0 to mu1, and the Wasserstein distance will be the minimal cost of doing so over all possible such vector fields. And so that defines a metric on probability measures, and so appropriate class of probability measures, and as with all metrics, it induces a geometry. And so the question is, how do I construct my analog, which is relevant to the Stein case, which gives me my gradient flow in the Stein case? And so before I do that, I need to define something. This operator tk rho. This is just basically an embedding operator, a kernel embedding operator, which if you give me a function phi, which is an L2, it just maps it into the RKHS. Okay, just in this way. So it's just integrating weighted by rho the pi. And so we need to keep this operator in mind because it's going to pop up everywhere. And it has some really important properties. And this is, as you can imagine, if k is smoothing and k is nice, then it's going to be a very smoothing operator, right? So imagine k was like a Gaussian RBF kernel. Then this is going to be, it's a bounded operator, it's compact, it's self-adjoint, it's positive definite. It has a set of eigenvalues which are going to decaying to 0. And so yeah, so this is, typically for normal kernels, this is a very smoothing operator. Okay, so how do we actually compute the geometry? And so what I'm going to do, what we do is we leverage something known as the Otto Villani calculus. And so this is really a methodology which popped up at the in the 2000s, and it was really a method to study certain class of equations which arise from fluid dynamics. But surprisingly, it's relevant in this context as well. So that's quite nice. And so when we construct a geometry on a space of objects, we typically need two things. We need to define what a tangent space is at every point. So that's like my set of directions that I can move in at every point. And then once I know what my directions are, I need to define an inner product on them, or a metric. And so my tangent space, really, it looks like a very horrific definition. So it's, you know, it's a set of distributions which can be written in this form here, such that V is in this set, but it's actually really easy to understand. If you recall the previous equation that I showed earlier, that's transforming probability, then this just describes like an infinitesimal step along that flow in the direction of V. And so V, what's V here? Well, V is in some sense your vector field that you're flowing along. And V is actually, has to be an element, it has to be an image, sorry, of this set here. And the key point is that it has to be an image of T. And T, recall, is a very smoothing operator. So in some sense, the set of possible V's is quite small because it's an image of a very nice smoothing operator. And so in some sense, there's not many directions in which you can go in. And associated with two directions, two tangents in the tangent space, we associate an inner product. And we should keep in mind that, you know, even though we're defining in terms of in terms of Xa here, we really it's a one-to-one correspondence with V. So, you know, we can just forget about this and just think about V instead as a direction. And so then the inner product between two tangent elements is just the corresponding RKHS inner product, because this is an element of the RKHS of U and V. Okay. And so that defines a metric. And then
with a question, Andrew.
Please.
I mean, usually I think of a Riemannian metric. I mean, a Riemannian manifold is a finite dimensional thing.
Yeah.
But the RKHS in principle could be infinite dimensional.
Yes, it could. But in this setting, it's a metric over the space of probability measures. So it's definitely not finite dimensional.
I see. Also, okay, it's a Riemannian-like kind of metric, but on an infinite dimensional space.
Precisely.
That's what I'm hearing.
Yes.
I see. Okay.
Yes. Yeah. In fact, so rho here would be the probability distribution at which you're taking the tangents.
Right.
Yeah. And so then, thank you.
Sorry, can I just ask a basic question as well?
Yeah, sorry.
On the last slide, what is curly D dash in the set?
Oh, sorry. Yes, it's a set of distributions.
Okay.
So generalized functions, basically. Yeah, it's just technical assumption.
Okay.
That
thanks.
it's yeah. So okay. So then once we're in this setting, then we can define the Stein distance to be very similar to the Bernoulli-Bernier formulation that we had before, but we just change a few of the distances. We change the norm here. So this just becomes the RKHS norm. The vector fields are now no longer are assumed to be images of this embedding operator, and we have the same constraint over the flows, that they have to map mu to V along this equation. And so we see that is very, very similar. And so basically, if I that will define not necessarily a metric, because because we are in because this is a quite smaller space, in some sense it's much smoother. In some sense, this distance is a little bit more myopic. If you imagine like VT is like your search space for flows which take you from mu to nu, then it's like, you know, at every point you have a lot less options to take. And because of that, there might be situations, although I'm not saying they do exist, but they might exist, where there's no way to go from mu to nu. And so in that case, we say that the distance is infinity. So we've not proved that it's a metric, we proved that it's an extended metric, so it can be infinity. That's, you know, something that, you know, probably one can then ascertain that it is a well-defined metric. It's just we never showed it. And so then, of course, then we actually need to define what a gradient with respect to the actual geometry is. I'm not going to go into that, but basically what this is, it's a transformation from like the fresh air derivative of your loss function. You transform it so that it's now on the manifold as an element of your tangent space. And so if you do that process, then you can actually show, and you plug everything in, you can show that basically your rho t is evolving. So once you plug in the terms, you can actually show that the gradient flow that you get by of the KL divergence with respect to this geometry is given by this equation here, but this was actually just the mean field equation that we had started from. So we basically established that that's the gradient flow with respect to this geometry. And so why do we care about this? Well, once we have this relationship, then we can start talking about rates of convergence. And so if we've established that these dynamics are actually a gradient flow of KL divergence in this geometry, the next step is to study, what's the curvature of this loss function KL divergence in this geometry. And of course, if it's convex with an appropriate rate, strictly convex, sorry, with an appropriate rate lambda, then you can probably say something about the rates of convergence. And formally you can. So if you can establish that this relationship holds second derivative for some lambda greater than 0 for all unit speed geodesics, so now it's a manifold, so you have geodesics at every point and in every direction, then informally you can show that you get exponential rate of convergence to equilibrium. So we wanted to set out to show this. And so I won't go through the calculation. You can actually work out the geodesics in both cases. And so what happens is that if you calculate this term here, the second derivative, you can show that it splits into two terms. The first term just comes from, it's just a term intrinsic to KL divergence, which is just the entropic regularization intrinsic in KL divergence. And the second one is actually dependent on pi itself. So this is going to depend on pi. This is independent of pi, basically. And so for Wasserstein, it was shown that this term, in some sense, it's non-negative definite. It can never hamper convexity in some sense. And then if you had some additional assumptions on the convexity of this, for example, that the Hessian of the log of the potential was, for example, positive, strictly positive definite, then this would satisfy that property. And so this condition here is, for example, what's known as the Bakry-Emery criterion, which gives you exponential rate of convergence. However, in the Stein case, we had bad news. This can actively be negative. In fact, you can easily come up with directions in which this is very negative. And so that means that you basically cannot guarantee exponential convergence in this sense, even for very strictly long concave measures. And so that was bad news for us. And that made it was unlikely that based on that it was not likely that we're going to establish a sensible condition under which you get exponential rate of convergence, at least in the sense of KL divergence. And so then I'm aware of the time, so I'll be very brief. The idea was then, okay, so what's the second next best thing that we can do? And that was basically to focus on situations where your initial distribution is very, very close to equilibrium already. And then you try and see, okay, so if you're really close, then is there any hope that I can get quickly to equilibrium, to pi, basically? So informally think of, rho naught would be some perturbation of pi. And you're trying to ask the question, if I'm really, really this close, am I going to converge quickly, at least at the basin? And so that condition can be expressed in this form, and you can actually express it directly in terms of the kernel, in terms of pi. And this condition is actually something which, for those who are familiar with, for example, Longevan dynamics, it's equivalent to something known as the Poincaré inequality. And in fact, this inequality here can be written in this way, where this is our operator L, and this is now a linear operator, which if I didn't have this term here, it would just be the operator that you get for Longevan dynamics. It's just the infinitesimal generator, but instead we have this smoothing operator here. And the condition we want to get exponential speed of convergence at equilibrium is that this inequality holds. And that is what we call the Stein-Poincaré inequality, because it's a direct variant or analog of normal Poincaré inequality if T was the identity. But problem is T is not the identity. That would be great. Instead, T is something which is really smooth and damping. So it's like you have your diffusion coefficient in your Longevan, like really small, really, really slowing everything down. And that immediately suggested that the rate of convergence is going to be dependent by the eigenvalues of this term here. And from that, I can quickly draw some conclusions. And the eigenvalues, of course, are going to be strongly related to the kernel that you choose. So the first result that we could show is that if the kernel is smooth, at least C11, for example, then you cannot guarantee exponential convergence to equilibrium to pi, even when you're really, really close to equilibrium already. And so basically this inequality only holds for when lambda equals 0. And so that means that you're not getting exponential convergence. The second conclusion is that if your kernel is translation invariant and you have some conditions basically on the tails of the translation invariant kernel, then the same condition also holds. And that's bad news. But that also means that it suggests that if I can construct a kernel which breaks these two conditions, then I have some hope of getting something which is competitive. And so this motivated us to look at, strictly in one dimension, I should add, this weighted Matern kernel. Now, of course, in practice, this is not advisable. But basically, what we do is we take a Matern kernel here. We weight it by 1/root pi x, 1/root pi y. And then if we have an additional condition on the log, negative log of pi, then we can show that the Stein-Poincaré inequality does hold in this context. And so at least in this context with this kernel, you get exponential convergence to equilibrium. And so I have some, and so that motivates us to consider a more general, almost singular kernel where you have exponential of minus x minus y to the p, where p is something between 0 and 2. And so some very simple numerical simulations, which I won't go into, suggest that actually this is beneficial. But of course, then once you're in the practical world again, we're talking about discretizations of ODEs. And then, of course, the analysis that we did doesn't take into account the stiffness of the ODE and the discretization error. However, nonetheless, if you make a good choice if you make a good choice of p here, for example, p equals 1, you see very superior behavior compared to when p is 2, which is the standard Gaussian kernel, which people tend to use in the literature for this type of algorithm. And so I definitely don't have time to talk about further work. So I will put that on the shelf and just say thank you very much for your time, and I welcome any questions if there are any.